Um, so what you're going to see here and throughout this series is that the history of this form and its relationship to the human heart. And um, I have to tell you, like I did yesterday, that I had no other intention other than trying to find a seven-sided form, and I couldn't find it with any mathematical applications. So I went back to my studies, which is art, and I discovered it artistically. So I'm going to tell this afternoon, I'm going to tell you how I decided that it was the heart, and what was it that I saw. Okay, so just to briefly start a little review. This is the bubble inside the chest of Haydn that becomes the left ventricle of the human heart that sits in our body like this. Okay, so the first thing I want to tell you is that when I presented the Flower of Life yesterday, the heart, the geometry of the heart fits in it, and it's the seed. It's the seed of life in the Flower of Life. Now that's very important that I was able to put it in there. And then I put a spear around that, which doubles the uh, assertion that it is in Flower of Life. It has two ways of showing that. Okay, so, but that doesn't show where the heart comes from. It just showed a relationship to the geometry that is extremely important, extremely old, and will be here until the end of the earth. But today I'm going to tell you, show you the geometry that the seven-sided form comes from, or where the heart comes from. This will help you understand what's going on with the heart like nowhere else, because this is lawful geometry. It's not meant based on any sentimentality about any kind. So in this presentation, I'll show you the geometry. I'll show you how I found it. I will show you how the heart sits in the body at 45 degrees. I'll talk about the valves. I will talk about blood flow, and I'll tell you what the heart needs. And then I will show you how it moves in two directions at one time. I have an example showing it, how it moves left and right at the same time. The heart does this, and it also moves from below to above, and it also moves forward and backwards. So that's what I'm going to do. So the first thing I'm going to do is to show you the geometry, because this geometry is the most significant geometry that I could possibly ever hope for to relate to our heart. And that's the vesica. And the vesica is based on three, not on two. We have the brain on right and left. The heart isn't based on two. The heart is based on three. All right, so if you're not familiar with the vesica, you will be in a few minutes. Because I've done this so that I can do it quickly. I could do it easily, in front of you, actually do the drawing, but it takes too long. So this orange almond shape in the middle, or kind of reddish or pinkish, is the vesica. And the vesica is made from two circles. And the two circles are identical, and you put the center of one on the periphery, and you put the other one on the periphery, and then you put the center in the periphery. So when you combine those two, you get the vesica. So the distance from here to here, and from here to here, and from here to here are three equal spaces without any ruler. They're perfect. Now that's amazing. All right, so the next drawing I show you, I'm going to add on to the drawing, same drawing each time. So the second drawing, I have drawn a green line and a red line. And that goes from the top of the vesicle to the bottom of it. And the green line goes from the outside to the other side. All right, so let's add some more lines here to our geometry. All right, now what we have is a triangle. Now the triangle has three sides exactly the size of the vesicle from top to bottom. The green's still there. Now let's see what else I can do with it. Remember, this is the human heart and its geometry and where it comes from. See, it doesn't come out of me. This is some fancy thing I made up. I didn't make this up. I couldn't do it. All right, here we go. Now we have another line at the bottom there that's the same length as the three red lines of the triangle. And if you take the red line, okay, and what you do is you put your compass here, or here, I'm sorry, put your compass here, and you swing an arc. And you swing an arc and stop that arc the same distance there is between across the vesicle. It's the same distance. That's why I made it green. Okay, now let's go to the next one. My gosh, now we have found the triangle and the kite, quadrilateral, and they are perfect in their relationship to the vesicle. So this distance that we went from here, well, this one, huh? We got that from the triangle. What about this one? This one came from the half of the vesicle, from the center of the vesicle to the top. You now have the chestahedron. It is now done. This is it. Can you imagine that? That is the geometry of the chestahedron. So the chestahedron has three kites and four triangles. So that means you have 4 times 4. You have 3 times 4, which is 12. And here you have 4 times 3, 12. This is just amazing. And the distance from here to here, this is 2. This is 2, and this is 2. This is 2, this is 2, and this is 1 and 1. So what you've got is number 6, no matter if you look at the kite or if you look at the triangle. So here we go. Here's the basis of the human heart. All right, this is amazing. Human heart is based on the vesicle and 2 lines. One's cut in half and the other one crosses the other. That is the basis of the human heart. That's where it comes from. Okay. To me, just constantly, I marvel that this is possible. That absolutely is okay. Now here's the complete chestahedron. This is what it looks like. It's an artistic drawing. And it shows you what I just did, except that completes it. And what I mean by that is that here's one kite, there's another kite, and here's the kite I showed you. Here's the triangle. Here's the other triangle. There's another triangle here, and a triangle on this end. 4 triangles, 3 kites. Now, notice that I have a circle around here, which is the same, which is the main circle, and then I have a circle here, and this circle and this circle are different sizes. Okay, so I also have that circle that goes around the vesicle. Now I'll show you why that's important. You take two circles, here's a half a circle, put the other half here, okay. And then I take another circle, now I'm using a sphere because we're now into the third dimension. We just left the second. So the vesica, okay, is cut from a sphere, and it looks like this. Remember, there's two spheres, so there's two vertices, or two vesicles, and there are the vesicas. That's the vesica, and inside there, between my fingers and the top fingers and the middle fingers, is the geometry of the human heart. Now, if I take these and I put them on here, they're exactly the distance between the kite's upper shape, which is triangular. It also goes all the way around the vesica perfectly. And there's that other circle. See it right there? Going around here. Think of that. It goes around the vesica and also is the determinant of the end of the kite. There's that same circle. That's amazing. See, these circles are based on the sphere that I cut the vesica out of. Now, here's another drawing that shows the tetrahedron in a sphere, and it's very difficult to draw a asymmetrical form in a circle or a sphere, but it's there. And then the kite here is flat, completely flat on this side. You can't see it. So we take what we call an oblique drawing and we extend the oblique drawing out, and there is the actual size of the kite. So the kite is on a flat surface. That's the only way you can get this. And of course, you know the distance from here to here because of the geometry that I just showed you. Now this side is a triangle, which is wild. This is on the opposite side. So it's also at an angle. So that's not true. So you have to make an oblique drawing. The oblique drawing gets right on the edge, and then you slide it over, and there is the triangle. So this triangle and that kite is this form. There's the circle, and there's a triangle, and then there's a circle inside the triangle. So try to remember this one. It was so, this is my discovery. But in the discovery, I saw that it was so close to the pentagram that I tried to draw it in the pentagram, and I did. And here's the first drawing of the tetrahedron. Now what I have is 3 stars, and it's so close that when I make this one, and I make this one, and I put them together, you cannot tell the difference with your eye. The difference is so small. Of course, maybe you're wondering, you know, what this looks like. So I'll show it to you. Well, I don't seem to have it. Maybe during the lecture I will find where I put it. But it's you can't tell the difference by your eye. Yeah, but it's not correct. You see, the tetrahedron does not have equal surfaces, but in its transition through its action of moving the blood, or the blood moving the heart, there is a perfect chastahedron. But the chastahedron that I'm presenting is not. But one of the characteristics that's so important to the Platonic forms too. So all the Platonic forms, I have a cube here. Well, I have an octahedron. Here's an octahedron. You notice that octahedron has all triangles. All triangles. There's 8 of them. And every triangle, if I go around like this, it's the same distance. If I go around here and here and here, it's the same distance as from here to here. So all of the shapes are the same length at the edge. Okay, so I will take the chastahedron. Okay, this is 2, and this is 2, and this is 2. So let's say it's 2 inches. So the triangle is 2, 2, 2, 6. That's 6. 1, 2, 3, 6. So now let's go over to the quadrilateral. Okay, this is 2. I'm sorry. This is 2, and the other side is 2. Get used to this. This is 2. This is 2, and this is 1 and 1. 6. 6. 6. That's how it's very important to relate to the Platonic solids, because it has that characteristic. This will also make a dual. All of the Platonic forms will go inside each other and also surround the same form. So it goes inside and the outside. So does this tetrahedron. It has an inside form and it has an outside form. So now you have a relationship to the Platonic solids, which are really important because they're the building blocks of the universe. There's only 5 of them. This is not one of them. This is not a Platonic solid. And the reason it isn't is because the Platonic solid always has the same shape all the way around. One shape. Triangles, triangles, triangles. No, not the tetrahedron. The tetrahedron has 2 shapes. It has a quadrilateral and it has a triangle, 3 and 4. So if you look at this, all right, this is based on Earth, and this is based on spiritual world, based on 4 and 3. 4 and 3 is 7. All right. One more thing about the Platonic solids that are fantastic. If you take this form and you take a cube, so what we got here is 8 triangles, and the cube has 6 squares. If I take half of the square, then I have 3 quadrilaterals, 1, 2, and 3. So this has 4 sides, and so does the quadrilateral, the kite. Now, if we go to the other side, I'm trying to find out where this is in the forms. I go to the other side, I go to the octahedron. And the octahedron has 8 triangles. The tetrahedron has 4. So half of the octahedron and half of the cube is the 7 in between. This is 8. This is 6, 7, 8. I'm going to get to the point here now, right into the heart. I'm going to leave a little bit of geometry, but I'm going to get into the heart. And what's so amazing about this is that maybe I should tell you how I decided that this was the heart. How could I possibly say that this tetrahedron is the heart? Well, one of the really neat ways that it came about was defining the shape, okay, of the human heart. And the shape of the human heart without the left ventricle, here's the left ventricle, the right ventricle, here's the left ventricle. So if I take this off, this is how it looks. And you can see, I mean, give me a break. So here's the tetrahedron. So one of the things I noticed was that I went to the library. My wife was working on her doctorate degree, and she went to the University of California in San Francisco, and I got the library card from her to get into the medical section. Okay. So that really helped me. I spent a whole year on those textbooks, 3 shelves, I went through every book that was dealing with any kind of projection or application of geometry to the heart. And of course, um, I didn't find it. So the first thing I did was when I found this tetrahedron, I thought it was a crystal. So I studied crystals like that. I said, no, it's not a crystal because crystals don't twist. Okay, so then I thought, well, why don't I go into plants? So I went into plants and I found the closest I could get to were buds, especially the rosebud. But I did a path curve study of the rosebud. It's not it. It wasn't any of the rosebuds or any of the plants that I went through. So then I went through the animal thing. And I looked, of course, no, of course there isn't any. So when I was outside waiting for my wife, there was a model of a heart. And I noticed that the model of the heart had this indication at the bottom that was different than this. It goes around like this, and then there's a point where it changes angles and goes like that. Oh, that's what this tetrahedron does. Okay. It changes at the bottom, okay, almost the same proportion as this. Oh, that really got me. So I thought, well, I got to look at this more. Now remember, I'm looking on the outside of the heart, but that's all I had at this time. It took me 2 years to figure this out. I didn't know it was a heart for 2 years. Okay, so another thing I noticed about the heart was that it had 3 lines. Now this is a model right out in the front of this university, the medical school. It had 3 lines that went up from the very tip up to here, and then when it got to this point, that line disappeared. My gosh, so I said right away, I knew, see, this is part of the geometry of the heart of the tetrahedron. It has a triangle, and then this part is it goes down to the bottom. So here's the triangle, and that's the angle. So when I put them together, they're like this. Yeah, look. So you can see that this part is connected to the quadrilateral, and then it goes up to the triangle and disappears. This line disappears. And that's exactly what the heart did. It ran up like this, and when it got to a certain point, it disappeared. And I thought, what is that? And so then when I realized was that if I put the tetrahedron in the cube, which you saw yesterday, those 3 lines that I saw on the bottom of the heart, which is called the apex, okay, these lines right here touch the face. All 3 of them touch the face. So that's why they're straight, and then they disappear into the triangle. So here's that part coming up on the bottom of the apex of the heart, and then it comes up and it disappears. And then why it disappears is because it turns into a triangle. So based on those 2 things, I took this seriously, that it could be the heart. So there's no explanation for that, especially all the studies I did and all the geometry that they did try to apply to the heart. That didn't work. Okay, so that's how I decided to start working on the heart. And of course, that took 23 years to get to today. So then I started to study, and I found out that everybody who's really seriously thinking about the study of the heart are these cardiologists that specialize, okay, in cardiology, not on operating or dissecting or anything like that. They're most interested in the research because the doctors are helping people to get well, but the researchers were the ones that had the meat that I needed. So I studied. I went online and found all these different agencies in Europe and America and Japan, all over, that do the research. And I found out that they backed up exactly. They were so helpful in what they did. And one of the things is that you can see that the heart sits at an angle. Okay, and it's exactly the same angle that it sits in a cube. So I looked at other ones, and then here was some guy, some doctor, and he found out that the heart sits, okay, at an angle, okay, and he even started to draw the cube. It's really great. He even started to draw it. Okay, but this line right here that he's got here is 45 degrees. He doesn't say that, but I can put my triangle on there. Okay, and so here's some other indication that the heart sits at an angle. This is the top view of the heart. Here's the side view, and here's the other side of the human being with an x-ray. Shows that, yes, it has all these angles. Okay, so, but there's no explanation for this. Matter of fact, even the angles that they have are wrong. Okay, so here it is. I went and got some x-rays of the heart. And this is where the diaphragm is. It's straight across. This is 45 degrees. This is 45 degrees. And this is 45 degrees. This is from the doctors. This isn't from me. Okay. But the problem is, okay, is they don't realize that 45 degrees that it's sitting in a cube is root 3. So you can see, if I show you this way, that's 45. The top also 45, and the other side 45. But 45 is not what the angle of the heart is. It is at root 3. Just like the tetrahedron is also in a cube at root 3. Now, why is that important? Because root 3 is formative forces, according to Steiner. He says that root 3 is formative forces. Boy, that sure fits for me, because that root 3 is right there. Okay, so there's another picture. And you see the reason that it sits on one side, one doctor told me, said the reason it sits on that side because this side of the body is colder than this side. Oh, give me a break. It's because it sits at a cube. So what I did is I said, okay, I'm going to make, this is fake, made out of paper. I made it out of paper. And here it is again. The reason it's on this side is because that's on that side of the cube. So I put the cube, I made this out of paper. Okay, so this isn't real. But I put the cube inside, and I put the tetrahedron inside the cube. And it shows why the heart sits over on this side of the heart, how the heart sits on this side of the body. So what I've been doing is doing my research, because I got to make sure what I'm doing isn't some kind of fantasy. What I'm going to show you is I showed to a doctor one time. I told a doctor came over to my house. It was from the Mayo Clinic. He was a surgeon, a heart surgeon. And when I showed him this, he couldn't believe it. So I'll show it to you. Now, the human heart, okay, from the top view, which is called the base. Okay, here it is. Here's the aortic valve. And here is the mitral valve. The blood comes in, comes out. Okay, so no one knows why these valves are this size. They don't. This valve is half the size of this one, according to my research. And so, how I came up with this is that if I take the Chestahedron and I spin it, there are two circles. There's a circle in the middle and there's a circle on the outside. There's a circle in here and a circle around here. The white circle in the middle is the mitral valve, and the aortic is right here. Oh, sure. There they are. There's the circle with the triangle spinning, the outside circle, and the inside circle is the inside spinning. And to put that over the heart, there it is. Okay, so here's your mitral valve, and here's your aortic, right here. Comes off the side. That guy, he couldn't believe it. So I guess he went back to the Mayo Clinic. I don't know. I never heard from him again. So here they are together. Here's the real heart, and here's the real heart. Look at that. He couldn't believe it. So the thing is, another thing is that the mitral valve, which is on the flat side of the base, the aortic is at an angle. It's not. They're not in line. This one's horizontal. This is down 135 degrees, I think. And so they don't know why it's at that angle, because there's no explanation for that. I found out that the reason for that is because the top of the heart is round. It's kind of round. So the aortic valve comes off the side of that round, and that's why it's at an angle. So this is what it looks like, okay, from the inside. So this is the mitral valve, and this is the aortic. Okay, and you can see this is at an angle. Why is that? Because this bows over. The base is round, okay? I'm getting ahead of myself, but you're going to see what this is. Okay, so this was another great indication geometrically. Okay, I'll go into that. You see, when you spin the tetrahedron, there's a shape inside. There it is. This is the shape. That's the architecture of the inside of the left ventricle. So, if I make it in reality, this is how it looks. That's the shape inside. Okay? So in the heart is like this. So this is the shape that the blood takes. But remember, we got to go blow in bubbles. We got to put this into minimum surface. So I did. I put it into minimum surface. And geometrically, this is what it looked like. Okay, that's that shape. All right, now I have to make this organic. So I do it. So that's what I showed you. Here it is. That's the organic shape. That's what the organic shape looks like. That was geometric. Okay. Now, what I did was I worked out the valve, the aortic valve, where the blood leaves the heart, makes an arch, and goes down. All right. So blood comes in, mitral valve, goes out, aortic valve. You see that angle right there? They have no idea about that angle, but they do know that they can measure it, and it's 135 degrees, just like this. And this is a like trough next to the septum where the blood leaves. So the blood comes in, comes down here, and goes out. Okay, so if you look at that inside the geometry of the heart, there's the whole heart, and that's how that looks inside, is what configuration that the blood takes from the architecture of the inside of the left ventricle. And you can see the mitral valve is twice as big as the aortic, and they don't know why. Because the geometry just shows you why. That's why this guy was so excited. All right, next, I guess I should show you, I'll show you how the blood runs, in through this. Okay, first off, I found out, I made this guy right here. This is the mitral valve, and this is the aortic valve. Okay, now, what I found is that the blood enters in a clockwise direction, and it leaves in a counterclockwise direction. Okay, and I did that by studying the valves. I looked at the way the cusps of the valves opened and closed on each valve, and I compared them. And I found out that they do a reversal, which is back and forth. So when the blood comes in, it comes in a clockwise vortex, and it leaves in a counterclockwise vortex. So how can I possibly show that? Well, I figured out how to do it. Now in here, there's no gears, there's no pulleys. It's very simple. Now you can watch. So if I turn this way, then that should turn the opposite direction, and it does. So this one is going clockwise, and one is going counterclockwise. There's nothing like this out there. All right. So then what I decided I would do is that why don't I show a model of what I have discovered so far with not only the shape, but has something to do with the way the blood runs. So if I turn this around like this, you can see that I have to get rid of this paper. If I turn it around, you can see that that's the inside shape, and then this is the aortic loop. This is what it does, and it goes down to the lower part of our body. Okay, so the blood comes in here. Okay, it comes in here, and then it reverses. So the blood coming out here should be a reversal of the blood coming in. Got arrows on there, now watch. Can you see that they're going in a different direction? Look, here are the arrows. See that? See the arrow here? Look at how I've been able to do that in the real geometry based on the human heart. Now, what happens is I've discovered that when it goes over the arch, it changes direction again. And so I was able to show that too. Now you watch this part right here, it's going to turn different. This one is turning this way, and the one inside turning the opposite way. See how this is going over, and this is going by those lines. So this is how the blood runs through the heart, okay? They don't know this, why this does this. They don't know how can I change the direction of this part and turn the corner and then make it go the opposite direction and have it opposite direction going in as it comes out. Where does this come from? This comes from the chestahedron in the heart. So I made a model to show that. The first model I ever made that showed the geometry of the inside and outside of the heart, inside a cube at root 3, I figured out how to get this to move. So it's not some static form. Even the geometry is not static. All right. But then made it even more realistic, because what I did was I was able to show that the inside of the heart turns in the opposite direction as the outside of the heart. Oh, come on. So what I did is I studied the myocardial fibers, and the fibers on the outside of the heart turn in the opposite direction as the fibers on the inside. And tomorrow, on Friday, I will show you how that works. But here we go. This is a model I made a long time ago, and this model shows the base. Here's the base, and the aortic is right here. Now remember, this base is round. Okay, so it goes down into this one. This is the inside of the heart. This is the outside of the heart, and this is the architecture that goes down to the apex. Okay, so both the outside of the heart and the inside of the heart go down to the apex. Okay, so that means that if I have this right, these should go in the opposite directions as the red ones. Okay, and so I was able to figure out how to do this, and it took a while, and this model took a while too. Okay, so you're gonna watch the reverse of the green and the red. Okay, you guys ready? Here we go. Can you see the red at the top is going in this direction, and the green on the bottom is going in this direction. At the same time, they're reversing at the same time. So this is what's happening from the inside and outside of the heart. These move slower than these. And why is that? Because this is a smaller diameter than this one. Okay, so that's the reason there's different speeds. Because this turns less than the turning in the opposite direction. It turns more. This turns more than these do. Now this was a hard thing to make, but I was able to do it. You know, tetrahedron, and I made it out of the pentagram. I knew I had it. Well, my hour is up. Friday, I will show you the myocardial fibers. What I'm going to show you. They have not put it together yet, and they have been working on it for 150 years and are still doing the same mistake. I will show you that, and I'm hoping this will help the cardiologists that do this research, because when you cut the human heart through an operation of any kind, you better know this.